All right, everybody, I think we're gonna get started. I'm just gonna mute everybody right now, but don't worry, you'll have plenty of opportunities to ask questions and interact later on this evening. But welcome. Thanks so much for joining us this evening for our World Above the Tetons speaker series. For those of you who don't know me, I'm Samuel Singer. I'm the founder and executive director of Wyoming Stargazing. So before I forget, I want to thank all of our sponsors for this evening. So I'm just going to share my screen so you can see all of the sponsors for the speaker series. Without them, we wouldn't be able to do this. So big shout out goes out to all of our sponsors, as well as the Wyoming Stargazing Board of Directors, who've been supporting the organization since the very beginning 7 years ago. So thanks so much to all of them. Before I introduce our speaker for this evening, just a couple things I'd like to show you on the Wyoming Stargazing website. The first is all the other virtual programs we're offering right now. We've got quite a few of them going on, including virtual stargazing programs. I'm going to show you a little promo video about that in just a moment. I'm also doing a bi-weekly show called Mind Bending Astronomy, which I'm sharing a little tidbit of some fascinating astronomy facts. We've got Sci-Fi Explained, also bi-weekly, where we take a popular sci-fi movie and dissect it for all of the true science and science fiction within it. And then finally, we've got Ask Dr. Sam, another bi-weekly program in which you can just join me on a Zoom call and ask me all your burning questions about astronomy. And that's been a lot of fun. Yeah, so do tune into those if you're not totally zoomed out from all the screen time that we're all engaging in right now. I know it's a lot, but yeah, love to see you on one of those programs. I do want to show you the promo video for our virtual stargazing program. So I'm just going to bring that up really quick. It's just about a minute and a half long, and these are some of my favorite virtual programs we're doing right now. So I hope you enjoy this little promo video. Well, welcome everybody to our virtual stargazing program. I'm Samuel Singer, the
Sam, we can't see anything.
Director of Wyoming Stargazing. Oh, thanks. Let's find out what's going on with that. Can anybody else see the video that's playing? Give me a thumbs up if you can see it.
No.
Like some people are seeing it. Thumbs down with some people. I'll stop the share and reshare, and we'll try again.
You have to reboot the thing?
No.
No. Let's try this.
You have to click up at the top at View Options and show that and share Samuel's screen rather than Doug Leonard's.
Interesting. So you guys didn't see the stuff on the Wyoming Stargazing website before either, huh? Interesting.
We did.
No, it didn't.
Some people did, some people didn't, it sounds like. All right, give me 1 second here. Let's see what's going on. All right, let's
See Sam.
see if this works. How about that?
Yep.
All right, let's try that. Well, welcome everybody to our virtual stargazing program. I'm Samuel Singer, the founder and executive director of Wyoming Stargazing. I want to introduce Mike Adler, who is actually doing the stargazing for us at his observatory just outside of Jackson. And we've got a bunch of cool objects we're going to show you tonight.
There it is. Wow.
Yeah, there you go.
Oh, that's pretty cool.
It's a crowd pleaser, right?
Yeah, right there. That's amazing.
clusters contain the most ancient stars in the universe. The stars made up of the stuff left over from the Big Bang. Oh,
There
we
it
got
is.
it!
There it is.
Ha-ha! Planetary nebula are the corpses of sun-like stars. This is what our solar system is going to look like in 4 or 5 billion years from now.
All right. So it's my pleasure to introduce our speaker for this evening. Dr. Douglas Leonard is a professor of astronomy at San Diego State University, and Doug and I go way back. Doug was my astronomy professor when I was in college 19 years ago. Kind of amazing that we're coming up on 2 decades since we first met. But Doug was one of the folks who inspired me to pursue astronomy. And so, yeah, one of the reasons we're all here tonight is because of Doug. And so I'm really excited to hear about what he has to share with us tonight about Betelgeuse and the rest of his research. So without further ado, Dr. Doug.
Thanks, Sam. Can you hear me, everybody? Thumbs up?
Sounds good here.
Great, great, great. Well, it's really wonderful to be here from my garage here in San Diego. And I want to thank Sam so much for inviting me to give a talk as part of the World Above the Tetons series. And when I went to the website to look over the speaker series, I was delighted to see that your past speaker last month was none other than Mike Brotherton. I hope many of you joined him. And his name rung a bell in my mind, and it rung a bell for a reason, and it's because 20 years ago, if I can advance the slide, there we go. 20 years ago, Mike and I actually co-authored a paper together. We haven't done another one since, but there it is from the archive, where Mike and I were studying an exploding star together that's known as a supernova. And since that time, we've kind of gone our separate ways. Hopefully, I think Mike gave you a talk last month, not just about science fiction, but maybe about some of the work he does with active galaxies and quasars. I've continued to study exploding stars known as supernova, though truth be told, almost all of my career has been spent studying stars after they explode and studying them with like the world's largest telescopes, and they're very faint and hard to see. But a few years ago, I decided a change of course was needed for my research, and the actual inspiration for why I decided to change course was because I visited Jackson Hole. So along with many of you probably, coming on 3 years ago, I witnessed my first total solar eclipse from atop Snow King Mountain, site of the future Wyoming Stargazing Observatory, right, Sam? Yeah. And the key thing about this astronomical event is, unlike usual, I actually dragged my family along with me to see this. I even wrote my wife in to see it, which at most, we have a deal, it at most happens once a year that she does an astronomy related thing with me. And there are lots of highlights in addition to just the eclipse. My kids met an astronaut. They still talk about this. Professor of astronomy is nothing compared to having ridden in the space shuttle. But lifelong memories for sure. But one of the real sort of profound discoveries that I had during that experience was just how neat it was to be able to actually see something with my own eyes, astronomical, and to be able to share it with other people and my family. And so I thought, wouldn't it be nice to actually study something where I can literally just point at it in the sky and say, that's something that I actually work on. Right there is Betelgeuse. That's something I study now. And it's taken a while. It's 3 years now out. And it was about a year later that I joined a team of international team of astronomers, affectionately known as the MOB. It originally stood for the month of Betelgeuse, but it's now gone on for years. And it's just a whole bunch of us who are interested in studying probably the most famous star in the sky, which is, of course, Betelgeuse. If you're not introduced already to Betelgeuse, it's this distinctly very bright red star, and it serves to demarcate the right shoulder of the mighty hunter Orion. Clearly, you all see a hunter in this pattern of stars. If you don't, maybe this helps. I'll have to say, this is about the only constellation where I can kind of see it. I don't see most of them, but I actually can kind of see a hunter here, having stared at this for so long. Once you see it, you really can't miss it. And Betelgeuse is like the most prominent member of this constellation, and it just stands out because it's so glaringly red in the sky. And you might think it would be easy to study, you know, usually it's about the 10th brightest star in the sky, but it turns out it's really hard to study something so bright. I'm used to using really large telescopes to try to peer into the depths of space and see the faintest things the universe has for me to look at. Here I'm trying to look at the 10th brightest thing in the sky, and it took about a year for my students and I to actually reconfigure the 1 meter telescope at our observatory, which is called Mount Laguna Observatory outside of San Diego. And it took about a year and many nights of struggling to try to figure out how to observe something so bright. I've never had this problem before, but I finally came online with studying Betelgeuse using our telescope at a very fortuitous moment. I actually was finally able to observe right at the beginning of this year in early January. And it turned out that that was a really good time to be coming online to study Betelgeuse, because it turns out Betelgeuse was doing something funny at that time. Betelgeuse isn't usually making headlines in the news, but along about the end of December and then on into January, it got a lot of headlines because it was acting strange. That's maybe not the astronomical term for it, but that's really what it was doing. It was doing something that it hadn't done before. And some of the headlines got pretty dramatic about this. Not only saying it was acting funny, but that it was coming imminently to the end of its life, and even possibly getting ready to explode. And as time went on into January, the headlines just got more and more kind of dramatic about this. And by month's end, it was getting kind of ridiculous. The level of fear they were trying to put into people about a star about to explode. I wasn't surprised that some unscrupulous people even thought it would be good to develop a Betelgeuse potion to help you in case it did manage to explode. The question is, why was there all this excitement? What was the flurry of excitement about? And to understand why people were getting so excited, you only have to go back about 1,000 years ago to July 4 of the year 1054. And what you'll find is that long ago, Carl Sagan was still alive.
Imagine the night when that colossal stellar explosion first burst forth.
A 1,000 years ago, people gazed up in amazement at the brilliant new star and wondered what it was.
Stars do explode. So the headlines were not that hyperbolic. Stars do explode. And if a star that's as close to us as Betelgeuse is actually exploded, it would be quite dramatic. Suddenly replacing the right shoulder in Betelgeuse would be a point of light, would still just be a point of light, but it would be now by far the brightest thing in the sky. It would have combined into that point the entire brightness of about a quarter moon. And it would be clearly visible during the daytime. And at night, it would cast its own shadows. It would be that bright. This is an artist's rendition of what it would look like if Betelgeuse actually exploded as a supernova. How did we get to this point? Why was there all this excitement? And why hasn't it happened? And when will it happen? So this is what I'm going to try to do tonight, is give you our best answers, the best answers we have to these questions. And I think a good way to begin is to just settle us all in and just remind us of our place in the universe, and then Betelgeuse's place in this universe, and why it would be so exciting if it actually exploded, and how we know that it will explode at some point. So let's first just sort of set up where we are in the universe, a little refresher. We live on planet Earth. Our planet Earth orbits the sun, and it turns out our retinue of planets orbiting a star is not alone. In the last 100 years, we've discovered that we live in a vast stellar system. It's known as the Milky Way galaxy. It contains over 100 billion stars that really are just like our sun, and they're all bound together by gravity, holding all the stars in the Milky Way galaxy. And our sun sits kind of out here in the outskirts of the Milky Way. It actually orbits around the center. It completes one galactic year every 250 million years. And at this point, you've probably noticed that this isn't an actual picture of our galaxy, but it's instead of an artist's rendition. It's a portrait based on our best guess of what the Milky Way would look like if we were ever able to send a spacecraft out of the Milky Way and get above it and take a picture of it. We think that's kind of what it would look like. We're nowhere close to doing that at this point. The distances are just so vast. And they're so vast that we actually measure them in terms of how long it takes light to travel. So let me just give you a quick understanding of just how vast the distances are, not just in our universe, but specifically in our galaxy. And we can start right at home with the closest astronomical object there is to us, and that's the moon. The only place we've actually landed and set foot, human foot. Yes, we have been there. To remind you, the moon shines by reflecting the light of the sun. And it turns out that our moon is about 200,000 miles away from us. And it takes light about 1 second to travel 200,000 miles. And so what that means is you're seeing the light coming from the moon 1 second after it hit the surface of the moon. And in fact, when you look at the moon, you're looking back in time 1 second, because that's how old the light is that's just now reaching us. So you could say the moon's 200,000 miles away, or you could say it's 1 light second away. And if we move on, the sun, like all stars, it's self-luminous. It gives off its own light. It produces its own energy. And it's about 500 times further away than the moon is. And if you do the math, what that means is it takes the light from the sun about 8 minutes to reach the Earth. So you might say the sun's 8 light minutes away. And what astronomers have discovered is that all these stars that you see when you look out at the sky are just like the sun. It's just like this. It's just that the sun is so much closer than they are. How much closer? This is a picture of the closest star that we've identified to the sun. It's known as Alpha Centauri, and it takes light 4 years to reach us. So when we look up and see the closest stellar neighbor to us, we're looking back in time 4 years. It means it's 4 light years away. So we return to this collection of stars that we call the Milky Way galaxy. And to give you a sense of scale here, from end to end, the Milky Way galaxy is probably about 100,000 light years across. The sun sits about 30,000 light years from the center. And the most distant spacecraft that human beings have ever sent, the Voyager spacecraft, the most distant spacecraft, been traveling away since the late 70s, is now less than 1 light day away from the sun. That's the greatest exploration we've done. It's now to 1 light day, roughly. So we're not even close to getting to the nearest star, let alone being able to take a picture like this. That said, sitting out here in the outskirts of the Milky Way, we have a wonderful perch to look out at the rest of the universe And when we do, we find that it's littered with galaxies, just like the Milky Way. Billions of them, and each one of them contains upwards of 100 billion stars. This is a picture of the closest major galaxy to the Milky Way. This kind of approximates what you'd see with your own eyes looking at Andromeda. It's about 2 million light years away. Here's a picture taken by an amateur astronomer. Wonderful picture of the Andromeda galaxy, and that's the closest one. It's a little over 2 million light years away. We find our universe is littered with billions of these, some would say, island universes, these stellar systems all bound together by gravity. And the finest resolution, the crispest, clearest pictures of these galaxies that we've ever taken have been taken with this, the Hubble Space Telescope, this orbiting observatory put in orbit around the Earth a quarter of a century ago at this point. And it takes the most exquisite images of the sky because it sits above the obscuring atmosphere. Here are some pretty pictures of galaxies. It's just amazing things to look at. 100 billion stars separated by millions of light years from each other for the most part. Now you're looking at 100 billion stars. A very small fraction of those stars, we estimate it's about 1 star out of every 400 that nature mints, will actually end its life by exploding. So most stars don't. Most stars die quietly or more quietly. Only 1 out of 400 is designed to explode at the end of its life. And that might not sound like much, but if you remember, if there are 100 billion stars in a typical galaxy like this, if you work out the odds, what you find is that a typical big galaxy should produce about 1 exploding star per century. And since there are billions of galaxies that we can see, a supernova is happening somewhere virtually every second, 1 per second roughly in the observable universe. We don't see or discover all of those, but we're now at the point where we do identify over 1,000 exploding stars per year. Let me show you what most of them look like. So this is a picture of a very famous galaxy. It's known as the Whirlpool Galaxy. It's about 23 million light years away. And this is a picture of it just sort of minding its own business, taken in the year 2011. And I just want to be clear what you're looking at here, because this can be confusing. These little dots here, these are stars in the Milky Way. So we're talking maybe tens or hundreds of light years away. And then plastered against this same backdrop is something that is 23 million light years away. It's all along the line of sight. So you're looking through a screen of stars in the Milky Way at this much more remote galaxy. And those stars are in general too faint and too close together in the sky to see individually. And so it just blurs into this nebulous whirl that we call actually the whirlpool here. So one day in 2011, one of its stars decided to explode. I say 2011, but really it's minus 23 million years, but let's not worry about the look back time here. One day in the year 2011, one of its stars exploded. And what that's going to look like to us is a new bright star appearing in the Whirlpool Galaxy. See if you can spot it. So you can look at both of those pictures, and the one on the right is after the star had exploded. The one on the left is before it exploded. And some of you may spot it, but in case you don't, it becomes much easier if you blink the images. So this is the before picture, that's the after picture. Now you see it, right? Before, after. That's the supernova right there, okay? We see these things all the time. So the question is, why all the excitement about Betelgeuse? The excitement is due to its proximity. It's not 23 million light years away, it's about 500 light years away. And Betelgeuse is exactly the rare kind of star that we think ends its life by exploding. It's called a red supergiant, and the name is actually appropriate, unlike most names in astronomy. The red because, well, it's red. You can see that when you look at it in the sky. And supergiant is because Betelgeuse is just a humongous star, both in terms of its size. If you took Betelgeuse and put it where our sun is, it would engulf all of the inner planets, including Earth and Mars, and probably all the way out to Jupiter in the solar system. That's how big the star is. It's also big in terms of its mass. It has, we think, about 20 times more mass than our sun does. It's a real heavyweight. And it's extraordinarily bright. It's giving off about 100,000 times the light that our sun does. So it's just enormous. These kinds of stars are very rare. 1 out of 400 or so is going to get like this. How do we know, how are we pretty sure that Betelgeuse is going to explode? Answer, we've seen it happen. We're now at the point in the last couple decades where in other galaxies, we see stars explode. And we were lucky enough to have taken really good pictures, often with the Hubble Space Telescope, before the thing exploded. And so we can actually see what the star looked like before it blew up. And let me show you an example, a really good example of this in action. This is actually a supernova from the year 2008. Astronomers are very creative in how they name supernovae. And that object right there is actually a supernova in this galaxy here. It's about 13 million light years away. And this is actually a picture taken with the Hubble Space Telescope. It's a real close-up, magnified, crystal clear image of the supernova when it was bright. And you can see these other stars around it, okay? But that's the supernova right there. And fortuitously, this galaxy had really good pictures taken of it prior to the star's explosion. And we only have this kind of information on about 24 supernovae. But what we find when we look right at the spot where the star is now a supernova, what we find is that, right where those lines are pointing to that star right there, that's the star that exploded. Now, this image here, the before supernova image, is actually in color. And that's because the images of the galaxy were taken using different filters. So we were able to process them and get a color image. This is a single filter image from Hubble Space Telescope. It has better resolution, but it's black and white. But you can line up the stars. Like that star is actually these two stars together. These guys here are these guys here. So everything's a little blurrier in this picture, but if you look hard, you can match the stars up. And that is the star that exploded. And we've done this now about 24 times, and every time the star looks just like Betelgeuse. And by looks like just like Betelgeuse, what I mean is it's red. Most stars are not red. And it's incredibly luminous. It's about 100,000 times the luminosity of the sun. That is, it's a red supergiant. In case you're doubting that that was the star that exploded, to remove any doubt, what typically you want to do is wait several years for the supernova to fade away and then get another picture and prove that the star is gone, right? Because if the star really exploded, it shouldn't be there anymore. And so there's the after picture to prove that this was the star that actually blew up. So this is what's been done now many times. And we always find that it's red supergiants. So we know the kind of star that explodes. Before this year, this was the kind of work that I spent a lot of time doing, okay? Painstakingly studying what are called archival images of supernova millions of light years away to try to derive the characteristics of the stars that exploded as supernovas. It's kind of like stellar forensics. Okay, you're going back to the scene of the crime and hoping to see something before the crime took place, where the crime is the star blowing up. Bottom line is we just kept finding that it was red supergiants that exploded. So you can see why the prospect of studying the closest red supergiant to us, Betelgeuse, was so alluring and so exciting. It's just sitting there beckoning us. So we have very good observational evidence that Betelgeuse is definitely worth watching. question is, when is the big event going to happen? And why did people get so excited earlier this year? To understand that, let's delve into the kind of the heart of the matter. And I say heart because what I mean is that the thing that triggers the star to explode is deep inside. It's in the core of the star. What's happening on the surface of the star is only an indication of what's happening in the core. So let's take a trip into stars and take a look at the cores of stars. So to understand how any star lives, and by living, I mean giving off and producing its own energy and light, we have to understand that there's a war being waged between opposing forces in every star. On one side, there's gravity. These stars have a lot of mass, and gravity's always trying to shrink them down, okay? If gravity could have its way, it would shrink them all down to a point. That's what gravity wants to do. But while a star is living, there's a very strong force that's pushing out against gravity. And it's basically the force of light itself. You don't usually think of light as exerting a pressure, but it actually does. And in the core of the star, there's a tremendous energy generator there, which makes a huge amount of light, which pushes out against the gas's gravity as it makes its way out the star. And that's what actually keeps the star puffed up. Opposing forces, gravity in, pressure out. It's a balancing act. For a normal star, like our sun, the energy generation is actually being produced by the simplest and most abundant element in nature, and that's hydrogen. Basically, when our universe started about 14 billion years ago, there was a lot of hydrogen, not much else. And stars are basically just big balls of hydrogen gas held together by gravity. And what's so simple about hydrogen is it has just one proton in its nucleus. It sits here at the top of the periodic table, bringing back memories of chemistry class for many of you. And what's happening in the cores of all these stars that have just been born, is that protons are basically whizzing around very quickly because it's so hot, millions of degrees, and occasionally two protons slam together head on so hard and so fast that they overcome the repulsion they feel because they're both positively charged particles, but they get together and they stick together. And when they stick together, they form a new element, the next element on the periodic table, which is helium, which has two protons in its nucleus. And believe it or not, when two protons jam together and stick together like that, a little bit of light is produced. And when billions of atomic nuclei are fusing like this every second, a lot of light is produced. And that's the secret. In the cores of stars, light elements are being fused together into heavier ones. And this process is what we call nuclear fusion. And that creates the light that pushes out against gravity and keeps the star puffed up and ultimately illuminates the universe. Problem is that at some point, you're going to run out of fuel. You're going to run out of hydrogen. And the good news is heavier elements than hydrogen, like helium, can also fuse. But they require higher temperatures because it took a lot of energy to get two protons to stick together. Now you're trying to jam together four protons, two protons plus two protons, slamming those things together. There's more repulsion from all that positive charge. And so you need even higher temperatures to fuse hydrogen or to fuse helium into heavier elements. But stars can do it. Our sun will do it one day. Right now it's fusing hydrogen into helium happily. But at some point, the hydrogen will run out in the core and helium fusion will actually start. And it produces elements like carbon and oxygen, heavier but further down on the periodic table. Funny thing happens next. After spending billions of years fusing hydrogen into helium and then helium into carbon and oxygen, 399 out of 400 stars are done. They can't fuse anymore. It just doesn't get hot enough to jam together all those protons to fuse heavier elements than carbon or oxygen. And so at that point, the star dies. And the star dies a very gentle, graceful death. this will be what will happen to our sun in 4 or 5 billion years. I think Sam mentioned this, or showed you this in the pre-lecture video. What they do is they puff off their outer atmosphere into space, and then what's left of the star compresses under gravity, and with nothing to stop it, it shrinks down by a factor of about 1 million in volume. It goes from something that was like the size of the Earth, the core of the star, and it shrinks down to something like the size of Jackson Hole, or maybe Casper. I don't really know my Wyoming dimensions too well. But it shrivels down into this fossil of the once brilliant star that gets supported by a weird quantum mechanical force dealing with electrons, and that's known as a white dwarf. And we see thousands of them littering our galaxy. Our sun's going to become one of these things. Nowhere in that story did we mention an explosion, and that's because all stars that do this were born with less than 8 times the mass of the sun. They're considered low mass stars. But 1 out of 400 gets born with more than 8 times the mass of the sun, and their fates are entirely different and more dramatic than that. What happens is they begin just like the low mass stars. They fuse hydrogen into helium, then helium into carbon and oxygen. But we have to make 2 points here. First, when they begin fusing helium into carbon and oxygen, the temperatures and the pressures are so great in the centers of these stars that the fusion rate goes way up, and the amount of energy pushing out against the outer layers of the star rises, and it starts beating gravity. And what happens is the star actually expands dramatically. And so when the star starts fusing helium into carbon and oxygen, the star swells up and becomes a giant star, okay? A red supergiant. This is a high mass star at the very end of its life. It's done with its hydrogen fusion in the core, and it's at least fusing helium into carbon and oxygen. So when you see a supergiant star, you know this is a star on the brink of coming to the end of its life. Betelgeuse. By virtue of the fact that it's a red supergiant, we know it's approaching death. It's at least fusing helium into carbon and oxygen. Unlike the low mass stars, though, these high mass behemoths can continue on past carbon and oxygen. In fact, they're able to fuse elements all the way up to iron. That's element number 26, has 26 protons in the nucleus. But they can't go beyond that, because the rules of quantum mechanics say nuclear fusion only gives you energy up to 26 protons. You try to fuse something heavier than that, it costs you energy. It doesn't liberate energy. And so even these behemoths, these high mass stars, eventually run out of fuel. And they run out of fuel when they've generated this iron core. If you could peel away the layers of one of these high mass stars right at the end of its life, what you would find is an iron core all the way in the middle, surrounded by the ashes of all the previous generations of nuclear fusion that kept the star alive, progressively getting to lighter and lighter elements until you end up with this big, massive hydrogen envelope still surrounding this core, okay? But once that iron core develops very quickly, I mean, in less than a day after it starts, okay, it becomes very massive and it can't fuse anymore. And so gravity is ultimately going to win, and it does. What it does is it collapses the iron core. In less than a second, the iron core goes from something maybe the size of Earth down to something really small, okay? You know, really small, like 10 miles across or so, until a new source of pressure is found. And actually, this object gets supported by the pressure of neutrons. What happens in the collapse is that protons and electrons actually get squeezed together to form neutrons, and you wind up with just a ball of neutrons in the center of this star. And that's something that actually gets called a neutron star. It's like a huge atomic nucleus. But it halts, and so the core just collapses down to this thing that we call a neutron star, And then the rest of the star implodes on top of that neutron star. And what happens then is all that material slams into that hard object in the middle, and then it somehow sends a shockwave out through all the material, and it gets ejected into interstellar space. And it announces its brilliance with over 1 billion times more luminosity than our sun has. And that is a supernova. And that is exactly the fate that we think awaits Betelgeuse, just like it does every red supergiant. The problem is the timing this event. We know, by virtue of the fact that it's a red supergiant, Betelgeuse is done fusing hydrogen in its core. That's about it, though. The problem is, helium fusion can happen for about 1 million years. And just looking at the star, we can't see the core. The rest of the stages go by very quickly. I mean, if Betelgeuse was fusing carbon in its core, it has a couple thousand years left. If it was fusing neon, it has about 6 months. If silicon, just a couple of days. But we can't see the core. All we see is the outside. But we get very excited if something strange starts happening to the outside of Betelgeuse, because it's the part that we can see. And that's what happened last December. Here's the story, okay, of what happened. People have been watching Betelgeuse for thousands of years. And it was first noted back in 1836 that Betelgeuse is not a steady star. It varies in brightness quite a lot. And for the past 100 years or so, we've watched it vary in brightness, sometimes getting brighter, sometimes getting fainter. We watched it intently doing this. I'm going to show you what's called a light curve of a star, which is just a plot that shows how bright the star is as a function of time. And this one's just going to show you the last 7 years of Betelgeuse observations. So here goes. Let me try to explain what you're seeing here. So this is called a light curve. And on the y-axis is the brightness of Betelgeuse. And on the x-axis is year. So you can see we begin in 2013, and we ultimately will get up to 2020. And each point here is an observation that someone made of how bright Betelgeuse was. And they're taken in crazy astronomers' units that I'm going to shield you from, except to say that right about here on the plot is the typical brightness Betelgeuse seems to have, and right here is about half as bright. So if Betelgeuse dimmed by a factor of 2, it became half as bright as usual, the points would be down here. Most typically, they're up around here. And what you can see is that there's, it's definitely varying quite a lot, right? It goes up, it goes down, all right? It's a variable star, as we say, all right? And in case you're wondering, what are these gaps? Are astronomers just lazy? Why do we have no information about Betelgeuse? It looks like it's the mid part of every year, like from May to August. There's just no data. It's not because we're lazy. It's because that time of year, Betelgeuse is only out during the daytime, and our sun makes it so we can't see Betelgeuse. So we can only see Betelgeuse when it's actually up in the sky at night, and that's in the winter months. So we miss data every year because of our sun. And we've actually just entered that for the year 2020. So I wish I could end the talk by saying, go out and look at Betelgeuse and see if it's exploded, but I can't because it's not visible right now. I can say go out in September and find out if it had exploded. What got everyone's attention right at the end of 2019, you can see I blocked out this part of the data. What got everyone's attention by the end of 2019 is that Betelgeuse started plummeting in brightness. When we have over 100 years of observations of this object, it never got this faint. By the end of 2019, it was well below half its typical brightness, ultimately getting to about 1/3. I mean, you could really see it. Literally, my kids looked up and said, what's wrong with Betelgeuse? It's really faint. I mean, it dropped from being about the 10th brightest star in the sky to like the 30th over just a period of a couple of months. So it's this precipitous drop in brightness that is what led to all the speculation that something weird was afoot with Betelgeuse. And this just continued through January, and ultimately even into February, okay? Although by the end of February, the press was getting a little tired of waiting around for this explosion. And one of my favorite things here is, you know, they had a story about something else, biggest cosmic explosion since the Big Bang spotted in distant galaxy. But then they just put the tag, no, it's not Betelgeuse, sorry. So at this point, everyone's getting kind of Betelgeuse fatigue, waiting for this thing to explode. The fact is, there was always a problem with predicting it was going to be exploding in the next few days. And that's, as you now know, because the trigger for what causes the explosion is deep in the core, not on the surface. And just because the surface was getting faint, was that telling us anything about the core? Theory doesn't have too much to say about this. Most theorists said probably not. Changes in the core generally are thought to take hundreds of years to manifest themselves on the surface, you know, or at least a year. Okay, it depends, I guess, what kind of pressure wave or whatever is set out. But the surface is not thought to be a great indicator of what's happening deep in the core. What's more, astronomers obviously got very excited about Betelgeuse behaving so strangely, and they were driven to look into the historical record to look to see, are any of these stars, these progenitor stars, the stars that explode as supernovae that we have in the record, do we have any observations of those in the years leading up to the explosion to suggest that they all plummet in brightness or do anything weird on their surface? And it's getting a little technical. Here's a paper that came out. The only part I want to draw your attention to is the fact that they found in the record 4 supernova progenitors, and with images leading up to the explosion, like years leading up to the explosion. And the bottom line is they found no significant evidence for stochastic or steady variability in those stars. These are the light curves of the stars, and they're flat. So it's not like every supernova was preceded by a plummet in brightness and then explosion. So observationally, this was telling us that we didn't think this was really telling us anything. By the beginning of this month, the press had kind of gotten hold of this, and they started, you know, saying, okay, guys, it's probably not going to explode after all. But the need for clickbait, of course, still exists. And so we do find articles still popping up. Running a Google search today, I found the most recent one of these is none other than the esteemed Jackson Hole buck rail. Okay. So even your local rag is not immune from this. But reports of the imminent demise have indeed tamped down. And it's not just from, you know, stodgy astronomers saying we don't think the surface tells us very much, but in fact, people observing Betelgeuse and getting light curve of it have found that it has now returned to its normal brilliance. It was an unusually deep dip, but now it's back in business at the same brightness that it typically has. And so there you are, Betelgeuse is back roaring away like it usually does. So a couple questions here. All right, so just when will Betelgeuse explode? Well, I had a nice little joke at the expense of the Jackson Hole buck rail, but I'll say they did get it right. And it's good they did, because this was actually an article about tonight's talk. And so here's what they had to say. They said, any day now or night, the red supergiant is expected to explode and go supernova. Any day, that is, within the next 100,000 years or so. So once you dug into the article, it got below the tagline. They got the science right. If I had to hazard a guess, I'd be even more conservative than that. I'd cover all the bets and say, in the next 1,000,000 years, it's going to explode. Because the helium fusion in a star, Betelgeuse's mass, that can go on for 1,000,000 years. If you really forced me to pin a date on it, I'd say most likely it'll be in about 100,000 years. And that's due to some kind of controversial evidence from the chemical composition of the surface of Betelgeuse that indicates a certain stage of being a red supergiant. So I'd say probably in about 100,000 years. But man, the uncertainty on this is great. It could happen tomorrow. It could be 1,000,000 years from now. So my status report on Betelgeuse remains, it's going to explode at some point, probably in about 100,000 years, but it wouldn't surprise me if it was tomorrow, and it wouldn't surprise me if it was 1,000,000 years from now. Second big mystery, why did it get so faint? I mean, we've been watching this thing for 100 years. This is the faintest it ever got. And we have some clues to answer why did it get so faint. There's an imaging technique that is really extraordinary that allows us to actually resolve the surface features of Betelgeuse. This is by virtue of the fact that it's so big and so close. And so it's one of the only stars that can be resolved where you can actually, it's not just a point of light, you can actually see surface features. And I'm going to show you two pictures of Betelgeuse. The first one is one that was taken in January of 2019. That's this one. So this is an actual picture of the surface of Betelgeuse. And just for context, if you put the Sun and Jupiter on here, they would be about the size of what you're seeing here, okay? Or they'd actually be about half that. It would be like from here to here. That's about the size of Jupiter's orbit, okay? So if it replaced the Sun, Jupiter would be just skimming the photosphere of Betelgeuse. But this was the picture taken in January of 2019 when Betelgeuse was kind of normal brightness. Another picture was taken about a year later, the end of 2019. And check this picture out. That's the picture. You want to see them blinked back and forth. Okay, there's January, there's December. Okay, something happened to the southern hemisphere of Betelgeuse. And basically we have two choices. Either it's the surface of the star itself that is just getting colder. Kind of think of it as like a huge sunspot. Sunspots are these blotches on the surface of the sun that emit way less light than the surrounding regions because it's cooler gas there. Betelgeuse is being such a big star, the sunspots are actually much bigger and they can cover a lot larger of its surface. They're called convective cells. And it's possible just a really huge one of these convective cells surfaced and brought the temperature way down. And so that's a possibility. It's another possibility. The other possibility is something's just blocking our view of Betelgeuse. And it's not like an alien spaceship or something blocking our view, right? We can still see it, it's just a lot dimmer. The best idea that we have for what could be doing that is dust. Same, just like the dust that annoys you in your own house. Interstellar space, the space between the stars, is littered with tiny little grains, solid grains of heavy elements, dust. Occasionally, a big behemoth star like Betelgeuse, for reasons we don't completely understand, but occasionally these big stars just sort of belch out a whole lot of dust and gas along with it, okay? And it's possible that Betelgeuse had such an eruption and that it's that dust that was dimming the light coming from behind it. We know stars do this. I'm going to show you an amazing picture of an even more massive star than Betelgeuse that about 150 years ago had a titanic eruption. And today we can study the material that's just been racing away from this eruption. Here's this picture. This is a star known as Eta Carinae, and the star is actually buried in here. It's still there. This wasn't an explosion, it was an eruption. It just sort of burped out all this material. And this dark stuff here is dust that was just erupted from this very, very massive star. We think it's about 100 times the mass of the sun in here. It's clearly having problems, clearly reaching near the end of its life also. While nothing so dramatic is thought to have happened to Betelgeuse, the basic principle of a lot of dust blocking our line of sight is a very active one that's being considered. So we have these two choices. Either the star itself got cooler, or there's dust probably blocking our view. And you want to know which one's right, but at this point, we don't know. Both are consistent with the observations. This is a very active area of research. And at the risk of just ending the talk by getting very geeky, I'm actually going to show you just a little of the data that we've been collecting at Mount Laguna Observatory. And I'm going to show you actually the very first piece of data we got back in very early January of Betelgeuse. Here it is. You're looking at the spectrum of Betelgeuse. This is the first one we got. So I was very proud of this. This was like 2 years of work to get this thing. So first of all, what is a spectrum? Isaac Newton taught us that if you take light and pass it through a glass prism, it disperses, it spreads the light out into its constituent colors. If you take what looks like white light and split it up into its colors, the colors here are what are called the spectrum of the object. And beginning in the 1800s, astronomers started doing this to starlight. They sent the light through a glass prism, and then they're able to see how bright is the star at every color. Now you'll notice my labels here, I say wavelength in some funny units known as angstroms. This is what astronomers use. But you could replace this with less, erudite labels. On the x-axis is basically the color that we're looking at. Violet light has short wavelengths, red light has longer wavelengths, and on the y-axis is just how bright the star is. And look, Betelgeuse looks red for a reason. It's giving off most of its energy at red wavelengths. So this is a spectrum of Betelgeuse on January 4th, 2020. Now, the beauty to an astronomer looking at this is actually all these up and downs, these little jig-jags in here that you see I've labeled, okay? These are being produced by elements in the atmosphere of Betelgeuse. Hydrogen, barium, magnesium, titanium oxide, sodium. And it turns out by studying the depths of these lines, these features, we can get a handle on the temperature of the surface of Betelgeuse. So we're still analyzing these data. We still have some that we have yet to even to work with. What I want to show you here are 3 spectra that we got, all over plotted, okay, on these different dates. Each of these represents a night of my life I'll never get back. But what you can see is it looks pretty similar one to the next, but there are differences. And what we're currently wrestling with is, are the differences that we see here enough to explain a temperature drop necessary to explain the dimming? And so there are lots of different data sets that people are working on trying to come up with an answer to this question. Some seem more consistent with the temperature drop. Some seem more consistent with dust. If I were betting, I'd bet with the temperature drop, but check back in a year, okay? The jury is still out on what caused the great dimming of 2020. So bottom lines, when will Betelgeuse explode? Sometime in the next million years, could be tomorrow. Why did it dim? We don't know, but we do have ideas. So like I said, invite me back for a status report in a year to find out. Or if Betelgeuse has exploded by then, you don't need me to tell you that it exploded. I think you can probably figure that out for yourself. All right, thanks. I'll sign off with that.
Thanks so much, Doug. That was awesome. You're getting a big applause there.
I like being able to see it, even in postage stamp.
Yeah.
It's very helpful to see that there are people.
Well, that was fantastic. I bet there are a lot of people who have some questions. And so we'll do some Q&A now. Don't leave just yet, even if you don't have questions. After we finish with some Q&A, we're going to do our raffle prizes for tonight. Everybody who is here is entered in the door prizes. And if you bought raffle tickets on top of that, you get a chance to win one of the amazing astrophotography prints. made by one of our board members, Mike Adler. So stick around after the Q&A for the raffle prizes. But if you do have a question, feel free to unmute yourself and ask your question to Dr. Doug.
Okay, well, I actually, this is Mike Adler, by the way.
Hi.
Hi, Doug. Great talk. I really enjoyed it. It was fantastic. Yeah, and so did my wife. We were watching Betelgeuse, and it definitely was a lot dimmer than you normally see it this winter.
You could totally see it.
Oh yeah, yeah. It was dim. I mean,
Very dim. Yeah.
Okay. The question I had though was, what causes the periodic variation that we see, which has been going on for forever? I take it. So maybe you could answer that question.
Sure. Yeah. Well, you won't be surprised to hear me say it's controversial. We know that Betelgeuse pulsates. It does actually kind of breathe. It grows bigger and smaller, bigger and smaller. And there are convective cells that bring hot material to the surface and then shoot it down back into the star. There is a periodicity to the light curves. If you look at that light curve, you can almost spot it. But if you run analysis on it, you find that I think it's about a 400-day periodicity to the ups and downs. Superimposed on a longer one that's like 5 or 6 years. The short answer is we don't know, other than the fact that high mass stars become quite unstable towards the ends of their lives and undergo this sort of instability portion. Now, we'd like to think it's just a simple pulsating star, but it's different. It's more than that. It's not just that it's expanding and contracting and expanding and contracting. It's more complex than that. And it's probably a bunch of different things happening. So I kind of sidestepped your answer by saying we don't really know. There's a lot to learn still about Betelgeuse. Not all red supergiants do this. So it's a bit unusual in that regard too.
So I take it is definitely not a Cepheid variable star, which is
no, it's not a Cepheid. Those are supergiant stars, but not to get too technical here, but they're crossing a part of the Hertzsprung-Russell diagram where Betelgeuse is not. Betelgeuse is not in what's called the instability strip. So Cepheid stars that Mike just mentioned are very famous stars that pulsate with a really fixed period, 10 days, 20 days, 30 days. And it's like the star is just breathing. They expand and they contract, they expand and they contract. And this is an understood portion of the lives of high mass stars that they go through. Betelgeuse is not in that stage. So it's not like a regular pulsating variable star like a Cepheid.
Doug, do we know why Cepheids pulsate like that?
We do. There's a pretty well established now theory for what's going on. So if you haven't heard of Cepheid stars, they've become very famous in the last 100 years because it turns out that they serve as very good yardsticks to measure distances in the universe. And so in addition to just being interesting from their physics, they're also just interesting because we can get distances using them. It has to do, let's see if I can remember my stellar astrophysics. It has to do with singly ionized helium in the atmosphere of these stars. And it has to do with kind of, there's a mechanism for energy to be stored up in the atmosphere of the star. It's like when the star contracts, it heats up and ionizes this helium, and then it heats up, and then the gas pushes out and expands the thing, and then they recombine, and then the process just continues over and over. And a real stellar pulsation expert would quibble with my simplistic understanding of the Cepheid pulsation mechanism, but that's it. It's basically this layer of ionized helium that is able to tap the energy and trap it. in this very periodic way.
Yeah, the amazing thing about Cepheids is that the frequency it pulsates at is proportional to its brightness. So that's how you can measure its true brightness, by measuring its frequency. Then you know its true brightness, and then you can figure out how far away it is, because the brightness drops as 1/r². So anyway, that was figured out by Henrietta Leavitt in 1916 or something like that.
Yeah, couldn't have said it better myself.
Yeah.
Looks like Oanne has a question.
I think you have to unmute yourself. There you go.
I did.
Cool.
So there's some small chance, but not a very big chance, that Betelgeuse's explosion and the caldera will happen at the same time, right?
And the what?
Betelgeuse and the
Caldera.
caldera.
Yes, there's some small chance.
You know the caldera?
No.
Oh, you haven't lived. Go drive around Yellowstone and you'll come back understanding what the caldera
Yes.
is.
Okay. Yeah. Is this the super volcano?
This is the super volcano.
Yeah. Okay. I haven't heard it referred to as that. Yes. There's two eruptions.
I think from our standpoint, it would be what you call your major bummer.
Yeah. That's about right. I think the likelihood is probably about the same. As I understand super volcanoes, their recurrence interval is similar perhaps to our understanding of when Betelgeuse will explode, like the next million years or so.
It was 560,000 years ago. Is that correct?
Yep. Okay, there you go.
Yeah.
Yep.
So somewhere in the next 100,000 years.
Yeah, the supervolcano would be much more devastating to life on Earth than Betelgeuse exploding.
Especially in this neighborhood.
Yeah.
Hey, Doug, great presentation. Thanks so much.
Thanks.
How do we get elements heavier than iron then, if iron is as heavy as we can get?
Yeah, that does kind of beg the question, doesn't it? Let me get back to your chemistry lesson here. Here it is. Okay. Yeah, so you can basically understand how the universe produced all the elements up to iron, because they can basically be produced by nuclear fusion in the cores of stars. And when stars explode, the fact that they explode is actually very important, because if they didn't, you wouldn't be here. Because all the stuff that makes up humans, like iron and oxygen and carbon, if they just got locked up in corpses like white dwarfs, there wouldn't be any out there to make people. So it's very good that stars find a way to explode. Your question is, how does nature produce all of these guys? And the first part of the answer to that is to remind you that these elements are generally very expensive. And that tells you there's not a lot of them. I mean, this is like gold and silver and platinum and so forth. And there's just not that much of it in the universe. Well, on the other hand, there is some. And we don't think that any of it was there 14 billion years ago. Our best guess and I say guess because this is not proven, but our best guess for how these elements came to be, a majority of them actually come from supernovae. In the explosion itself, there is for a brief period of time, there is a very rare circumstance. Remember I said that you can't fuse heavier than iron. So if you try to take a proton into an iron nucleus and get it to jam in there and produce cobalt, okay, ain't gonna happen. Okay, the electrical repulsion is great, and the amount of energy, it takes energy to do it. So nature does not favor that to happen. On the other hand, for the brief moment right after the explosion, think about the conditions you have. I mentioned this idea of a neutron star being formed. So there are all these free neutrons. That's very rare. Neutrons aren't usually free. They're usually bound up in atomic nuclei. So you have all these free neutrons whizzing around in the same vicinity as where you have iron nuclei. Neutrons can enter those nuclei for free. They're neutral. They don't have a positive charge. So they can just bombard iron nuclei and create really humongous, they're called isotopes of iron. In other words, an iron nucleus with 26 protons and way more neutrons than it's supposed to have. And then quantum mechanics takes over and says, I don't like having so many neutrons. And guess what it does? It switches a neutron, it changes it into a proton, spits out an electron and something called a neutrino. And once a neutron is changed into a proton, what do you have? You have a new element. It's alchemy. It's a very sneaky way nature is able to generate heavier elements in the aftermath of a supernova. It's called neutron bombardment of iron and other very heavy nuclei. Basically, you bombard these nuclei with neutrons, create these very heavy isotopes. The neutrons then decay into protons, and that forms the new elements. So the aftermath of a supernova is where we think a lot of these elements come from. There are other mechanisms. Other kind of rare things that can happen might be responsible for producing specific elements in here. Like having two neutron stars collide or something can actually generate some of these elements too. So there are processes that we think produces these heavier elements. Unproven, but the theory is pretty good. Most people believe that's where the heavier elements come from.
Thank you. Thank you very much.
That goes along with the, your Carl Sagan's comment, right? We're all made of star stuff.
Yeah, literally. He wasn't just being glib.
Right. So can you just push this a little bit and just in terms of, one of your slides had type 2 supernova, and I know there's type 2.
Yeah.
And on the other hand, I know some stars obviously end up going into black holes and some don't. Maybe maybe make a comment about that as you've talked about, star life and death.
Right. So yeah, you picked up on a little bit of the jargon I was trying to shield you from. So you'll notice that this is a paper I wrote some time ago, studying a type 2 supernova. That must mean there's also a type 1 supernova. Is your question about different types of supernovae, or is it more about what becomes of the star after the explosion?
Oh, well, I guess whichever you think is going to be more interesting for everybody.
Okay, I'll bite and say that probably more interesting is going to be what becomes of these things after the explosion. And you can ask me the other question too. But yeah, so the process I described leaves what's called a neutron star at the end of the whole thing. And I think I actually, during the talk, I realized I was getting ahead of myself. Just to correct the record, it's the neutron star that's about the size of Jackson Hole or Casper, Wyoming. The white dwarf that I described before is more like the size of the Earth. So during the talk, I realized I got ahead of myself. I was thinking about neutron stars when I was really talking about white dwarfs. So white dwarfs are carbon-oxygen corpses that are about the size of the Earth and about the mass of the sun. So very dense things. And those are left by stars like our sun. That's the fossil that's left. High mass stars, the process I described leaves behind a neutron star. It's just a ball of neutrons about the size of a city, about the mass of 1.5 suns or so. Okay, and we've now identified upwards of 1,000 neutron stars, and sometimes associated with places where stars have actually exploded. Actually, that supernova of 1054 that I opened with, we've identified the neutron star in that supernova remnant. It's called the Crab pulsar. You referred to the final of the 3 corpses that stars can leave behind, and the third one is a black hole. And a black hole is basically just gravity's ultimate victory over the star. I mean, in some sense, gravity didn't quite win with either a white dwarf or a neutron star. I mean, it did a great job. It shrunk this huge thing down to something really tiny. But what gravity really wants to do is shrink the thing down to a point. And we think in the heaviest stars, probably stars born with more than 40 or 50 times the mass of the sun, that the collapse ultimately gives you something in the center that has too much mass for even the extraordinary pressures of support that neutron stars can withstand. There's probably some upper limit. We probably won't ever discover a neutron star with more than about 3 times the mass of the sun. You pile more mass onto it than that, and gravity just wins and collapses the thing down to a singularity. And that's the object that has been given the name black hole. And for a long time, it was debated whether nature actually produced black holes. I mean, they existed on paper, in theory, but by about the early 1990s, the evidence became so convincing that black holes did exist in nature. And they exist from stars, deaths, those black holes, okay? So, yeah, 3 different stellar corpses, a white dwarf, a neutron star, and then the ultimate demise is a black hole.
What is there? Can't pronounce that guy's name. Astronomer, the Indian astronomer,
Chandrasekhar.
Yeah, he had a limit, right? Is that the limit you're talking about in terms of?
Yeah. So Subramanian Chandrasekhar, brilliant Indian astrophysicist. Basically, in the 1940s, calculated, according to the rules of quantum mechanics, that there was an upper limit to the mass of a white dwarf. So these low mass stars that leave behind white dwarfs, he discovered an amazing thing about white dwarfs, and it's just a fun little thing. A white dwarf, I've been kind of dancing around, you're asking the good questions, I've been dancing around saying the phrase electron degeneracy pressure, because that usually makes half of the people leave the talk. It's actually the force, it comes from quantum mechanics, that electrons are not allowed to be squished too close together. And they resist being squished with a tremendous outward pressure. And what Chandrasekhar determined is that if you add mass to a white dwarf, a strange thing happens. It actually shrinks in size. I mean, if only other things work like this, like human bodies. If I ate 10 donuts a day and I shrunk in size, life would be really good. But it doesn't work that way. But a white dwarf, the more massive it is, the smaller it actually gets. The electrons actually get squeezed closer and closer together to resist more and more of the gravity. And what he concluded is that there's actually an upper limit to how much mass this quantum mechanical force can even support. And it's about 1.4 times the mass our sun has. And so he declared, you will never discover a white dwarf with more than 1.4 times the mass of the sun. And that's become known as the Chandrasekhar limit. And we've never discovered one with more than 1.4 times the mass of the sun. That's for white dwarfs. Neutron stars have a similar limit, but it's not as well established. And it's because we don't really understand, it's called the equation of state, of the neutron star material as well as we do the white dwarf material. It's thought to be somewhere around 3 times the mass of the sun, the absolute highest mass that a neutron star could have. And indeed, we've never found one with more than 3 for sure. And we rarely find one with more than 2 times the mass of the sun. And the black holes that we find have more than 3 times the mass of the sun.
Thank you.
Any other questions for Doug?
Well, I was just going to say that, you could talk about the type 1A supernova, what happens when you add more mass to a white dwarf.
Yeah.
And then something bad happens then, too.
Yeah, so I kind of begged the question there. It says type 2, there's obviously must be a type 1 supernova, and there is, and that's what Mike just mentioned there. It's a type of supernova known as a type 1A, and it's a different mechanism than the kind of explosion I've been describing. The kind of explosion I'm describing, it's a high mass star left to its own devices, explodes at the end of its life. It's like the inevitable conclusion of its life. Turns out there is a way to make a low mass star end its existence by exploding, but it needs help. As far as we can tell, it can't do it on its own. And as Mike was just saying, it comes from actually adding mass to a white dwarf, we think. Basically, this thing that a white dwarf, it's made out of carbon and oxygen. And if you want to think about it this way, it's actually like a bomb waiting to happen, because carbon and oxygen are fusionable material, right? Given the proper density and temperature, they can fuse into heavier elements. And what stopped them from being able to fuse was that the densities and temperatures were just never high enough in the low mass star. And so they created this white dwarf. But if you start adding material to the white dwarf, what happens? It shrinks. It gets more and more dense. And as you approach the Chandrasekhar limit, there comes a critical point where the density gets high enough to reignite the star. But it's not like an ordinary star. It's a white dwarf. And you bring that thing back to life, and you get carbon and oxygen suddenly fusing. It's not going to just fuse stably for 1 billion years. It goes off like a bomb. It rips through the whole star all at once. And so basically, you just have this uncontrolled thermonuclear reaction that just rips apart the white dwarf, and it explodes. And that is what's called a type 1, or more exactly a type 1A supernova. It's an exploding white dwarf. So our sun is not going to do that because, as far as we know, it doesn't have any help. The help usually is from another star, we think. If there are two stars that get really close together and they're orbiting with each other, and one of them becomes a white dwarf, the other one can feed it, can dump material onto its surface, and that's what builds up the mass and triggers the explosion. Our sun is all alone. It doesn't have a companion. So as far as we know, it's going to die a white dwarf and not explode. So type 1 supernovae from white dwarfs. There are dozens of subclassifications, and just be thankful I'm not subjecting you to type 1b, 1c, 2l, 2p, 2n, 2np. It goes on and on. Basically, though, there are two kinds of supernovas: the high mass stars and the exploding white dwarfs.
Any last questions for Doug before we do the raffle prizes? Yeah, go for it, Orion.
I can't find my raise hand clicker thing.
I hear you.
Back at the picture of Orion, where it's placed with, there we go. And then down here, there looks like a redder star, a more red star.
Yeah.
What's that?
This is actually what's called a star-forming region. So this is actually called the Orion Nebula, right here.
Okay.
And if you could zoom in on it, and I apologize, I wasn't anticipating that question, so I don't have my picture of the Orion Nebula on hand. But if you could zoom in on here, what you would see is that it's a very fuzzy patch of space.
I've seen pictures of it.
Yeah. That fuzz is interstellar gas and dust that is forming right now new stars. New stars are being born right here. All right. So it's kind of like a stellar nursery, you might call it. And there are baby stars inside the baby, meaning 100,000 years old, inside the Orion Nebula. And I'm sure on one of Sam's stargazing nights, he can show you the Orion Nebula. It's one of the prize things to look at through a telescope. It's beautiful to look at. So that's a star forming region right there.
Okay.
One of the interesting things about Betelgeuse is one of the things I didn't tell you is that these high mass stars don't live very long. Like our sun has been around for 4.5 billion years, and we think it has another 4 or 5 billion years to go. Betelgeuse has probably only been around for about 10 million years. 1/1000th the lifetime of our sun. They burn bright and live quickly. And so that means it was born only about 10 million years ago. And so it's considered a very young star, though it's old in the sense that it's about to die. But high mass stars just do that. And there's a lot of speculation about where Betelgeuse was born. It has some unusual properties. There's thought that it was kind of born there, in addition to the Orion Nebula. This whole region around here kind of is a star-forming region. And Betelgeuse seems to have been sort of ejected from the star-forming parts and is kind of has a very high space velocity. But being so young, it's moving through space quite quickly, actually, away from its birth spot. Anyway, yeah, this red patch here. The red is actually due to the element hydrogen, if you want to know the specific why it looks red. It's not red because it's like a color temperature like Betelgeuse is. It's red because hydrogen, that interstellar gas that surrounds all the new stars, if you excite hydrogen atoms, they glow the color red, basically. And so that's why it appears the same kind of red color. But yeah, go to one of Sam's stargazing nights. They'll happily show you the Orion Nebula. When it's
Only in the wintertime.
Yeah.
All right, well, let's draw some raffle prizes. And once we do that, if there are any last burning questions, maybe Doug can answer a couple more before we end for the night. So we'll start with the door prizes that everyone here has a chance to win. First, we're going to do this cool eclipse sticker produced by Holly Sage Art. And I'll pull a raffle ticket here for that. We've got Michael Schwartz. All right, we're going to do another sticker here. One of these eclipse stickers, also made by Holly Sage Art for the second door prize. We've got Arthur, can't quite read the last name, Arthur Carnesi, maybe? Congratulations, Arthur. Now we've got one of our 5 milliwatt laser pointers. These are a lot of fun. You can actually point out stars in the night sky with these. Definitely tools, not toys. And we've got Virginie Ratchert. Congrats. Also have, one of our commemorative eclipse coins from the 2017 total solar eclipse here in Jackson. We've got Scotty McGee. Congrats, Scotty. And last but not least, for the door prizes, we've got one of Mike Adler's framed astrophotography prints. There's some weird reflection there, but I think you can see it. It's a pretty amazing galaxy print. And the winner of that framed print is Tracy Helburn. Nice work, Tracy. All right, and now for the raffle prize. We're gonna give away another one of Mike Adler's prints. Let me show it to you here. This one is of the Veil Nebula. Really gorgeous print here. And the winner of that will be JR. I think JR bought about 30 raffle tickets tonight, so that's what you get. Well, congratulations to everyone on your door prizes and raffle prizes. And if there are any last questions for Doug, feel free to ask those. But if not, and you got to run, thanks so much for joining us tonight. And we do have a couple more speakers lined up for June and July. We'll get that information on our website in the next few days. So check that site to find out who the next speakers are and the days those will be taking place. And hope to see you then.
I might just add, this is Mike Adler, I might just add, it may very well turn out that next Friday is going to be a clear night. So we might very well do a virtual stargazing event with using my telescope. So stay tuned to the website, and Samuel will announce it if it turns out we do it.
Sounds good. Thanks for mentioning that, Mike.
Yep.
Any last questions for Doug?
I'd just like to thank, this is Steve speaking. I'd like to thank Doug for turning you on 20 years ago and making the night possible. Thank you, Dr. Doug.
You're welcome. Sam did not need very much encouragement. He came locked and ready to go.
I hope he comes back next year.
I met him.
Wonderful program. Thank you.
Yeah.
Thank you.
Thank you.
Yeah, thank you, Doug.
Thank you, Owen. Thanks for your questions, too.
Yeah. Let's hope Betelgeuse hasn't exploded by next year and the caldera stays underground.
Yeah, let's hope. I'd want Betelgeuse to explode in about September.
Really?
We probably would know about it before then if it did, because we now have gravity wave detectors and neutrino detectors that might actually get a signal from a exploding star like Betelgeuse.
Oh, so we'd get a lead time, huh?
Might actually get a little lead time.
Good.
Well, it wouldn't be lead time. It would be, we wouldn't be able to see the explosion visually, but we would find out, I think, we would find out that something had happened.
So, last question. So, in terms of neutrino detectors, I mean, we have a trillion neutrinos going through us each second, but apparently if Betelgeuse is going to explode, the neutrinos would be exponentially more than that, right?
Yeah, they're bigger and they're kind of a different energy than the neutrinos that are going through you. Most of the neutrinos going through you are from the sun. And a supernova's neutrinos are kind of a different flavor. And we have detected neutrinos from one supernova so far. It was in 1987, called Supernova 1987A, and I believe 11 neutrinos were detected by detectors on Earth. And that supernova was 160,000 light years away. Betelgeuse is 500 light years away. So our detectors would be flooded with neutrinos from such an event. So yeah, even if Betelgeuse explodes while it's behind the sun, I think we'll know about it and we'll be really angry that we can't see it.
No.
And then when it comes out, when it comes around, when it peers out from behind the sun, we'll see it again. Yeah, it got really hard to observe right towards the end of April for two reasons. First, it was disappearing behind the sun. And second, I had to get special dispensation from the Dean of the College of Sciences to be even able to go to the observatory in a global pandemic and get data. So it was a lot of fun zooming from Mount Laguna with my team. And I was the only human within 5 miles, which is what they wanted. But we did get it right before it disappeared. And we now have several months to analyze all this.
Thank you very much. It was great.
Yeah.
Look forward to having you come back again. So, glad you and Sam have a great connection, and hopefully he can be back to next year's
An annual event. Betelgeuse update.
Just have another total solar eclipse.
There we go. We'll try.
Why don't you invite him back for Thanksgiving time when Orion is in the eastern sky?
Sounds good to me.
Always sounds good.
Thanks a lot.
Thanks a lot. Take care.
Take care.
All right, Doug, I want to let you get back to your family. Thanks
Okay.
so much for being here tonight. I really appreciate it.
Thanks, Sam. It was a lot of fun. Great,
Yeah.
great crowd. I'm happy you're able to get so many people to come to a virtual talk.
Yeah, me too. I think it's
well
testament to how exciting this is for most folks.
Now, it's testament to your organizational skill too. So, good job.
Thanks. Yeah, pleasure seeing you as always.
All right, Sam. Thanks so much.
Yeah, take care, Doug.
Yep.
Bye.
Bye, Doug. Bye, Sam.
Good night, everybody.